So we have y equals to x squared times ln of x. And because ln of x does not take 0 or negative numbers as arguments, I mean, it's not defined for 0 or negative. So the domain of this function is only for x positive. That's something that you have to keep in mind. Domain is 0 to infinity, where 0 is not included. Another fact about this function that you have to know is that if you send limit x going to 0 plus this is yeah, I guess this one I should provide to you. So later on in Calculus 2, you're going to learn something called L'Hopital's rule. And using that, you can show that the limit of this function is equal to 0. So that's something that you haven't learned yet. So I'll just say this information is given to you. But given those information, our goal is to figure out the graph of this function. Okay, so let's try to find the first derivative. The first derivative is this. I have to use the product rule because it's the product of two functions. And x squared divided by x leaves you with x. And as you can see here, x is a common factor, so you want to factor that out. I mean, this is already a derivative, but you want to simplify as much as possible because you're trying to use it for drawing the curve. Now let's try to find the second derivative, which means I have to differentiate this, but this is again a product of two functions of x. So you need to use product rule. X differentiates to 1, so you only get 2 log of x plus 1 from the first one. Now, for the second one, when you differentiate 1, that's a constant by itself, so that goes to 0. That becomes 0 when you differentiate. But this 2 is a constant multiple, so it still is there as a multiple of the derivative of this log of x. Log of x differentiates to 1 over x. And as you can see, this x and that x cancels each other. Let me use a different color. These two x's cancel each other. And therefore you get 2 ln of x plus 3. Okay. Those are the derivatives. Now let's figure out the sign of this y prime and also the sign of y double prime. We want to find the intervals where this is positive and negative, also the same for this one. Okay. To do that, you first have to figure out when it's equal to 0. So let's see. For y prime, you have 2x times 2 ln of x plus plus 1 equal to 0. When is this equal to 0? Either when x is 0 or 2 ln of x plus 1 is 0. Those two things are multiplied. Yes?
How'd you get 2 ln plus 3? I got plus 2.
Oh, x and x cancels. There's a 2. 2 plus 1 gives you 3.
Okay.
Okay. So we have this, and then 2 ln of x equals to negative 1. Ln of x equals to negative 1/2. And you have to remember that to get rid of ln of x, you have to exponentiate both sides by e, because that cancels ln, leaving you with x equals to e to negative 1/2. Now, if you are curious about the value of this, you can try to rewrite this as 1 over e to the 1/2 power, which is 1 over square root of e. So, I mean, think about square root of 2.7. I guess it's about 1.6. 1 over 1.6. That's some decimal, slightly bigger than 1/2. 0.6, I guess. Okay. But that's not necessary. You just have to know it's some positive value. Right? We all know that e to any value is always a positive number. And also e to 0 is 1. So if you have an e to negative value, it will be something just less than 1. Okay? So if you knew that, that's good enough. Okay. Now, and then about this one. Although x equal to 0 is a solution to, it seems like a solution to this, but it's not really a solution, because when x is 0, what happens? Log of 0 is not defined. So this is a fake solution. You know, when you're solving equations that involves logarithms or fractions or square roots, every time you get the solution, you have to put it back into the equation to see if it's a solution or not. And this is the case when you get a fake solution. You figure out it's fake by plugging. Another thing is, we already know that the domain is from 0 to infinity, so this is not even in the domain. So that's another way to say we don't care about this one. Okay? So the only 0 that we care about is this. And now let's draw the number line. And again, we only think about points after 0. So 0 is not included in the domain. And here is e to the negative 1/2, which is some value that's less than 1. So I guess I can use 1 as one of the test values. Okay. All right. Now, what should I do for? So we have to evaluate this function for some value left up here, and because ln and e cancels, probably the test value you want to use over here is e to the negative 1. Negative 1 is less than negative 1/2, so this number is definitely less than that. And this is handy for us because when you plug it in here, e and ln cancels and you get a very simple value. All right, so let's try to figure out what happens to y prime when x is set to e to the negative 1. That's e to the negative 1 times 2 times ln of e to the negative 1 plus 1. This is 1 over e. Negative 1 part means 1 over e. And ln and e cancels, giving you negative 1. Negative 1 times 2 gives you negative 2 plus 1. So you get negative 1 over e. So you get a negative value. Yes?
Why do we plug it into we always plug it into the y prime?
Because this is the point where y prime is equal to 0. And we are trying to figure out at what intervals y prime is positive or negative. So the way you do that is first identify the points where y prime is undefined or it's 0, because those are the places where the function could change signs. Okay? And once you identify them and put them on the number line, you pick test points from each interval. See, because we only have one critical point, we know that the entire number line or the entire domain is divided into two parts, before and after that one critical point. And we just need to know what the sign of that y prime is before this point and after that point. And just like testing samples of water, you test it at a point, and that will determine whether this entire thing gives negative value for y prime or positive value for y prime. That's what we're trying to do. Okay. So y prime now for 1 is 1 times 2 ln of 1 plus 1. What's log of 1? 0. Okay. Log of 1 is 0, so you get 1, which is positive. So we found out that y prime is negative here and positive. Okay. I decided to erase some of this to have more room. Let's erase. Just write down the results that we found so far. We found out that before y prime is negative, and after y prime is positive. That's what we figured out. Now we're going to erase all this. Work on y double prime. Y double prime is 2 ln x plus 3. Let's figure out when that's equal to 0. That means 2 ln of x equals to negative 3. And move the 3 to the other side and divide 2 both sides to get ln of x equals to negative 3 over 2. Now what do you do? Take e of both sides so that ln and e cancels, and you get x equals to e to the negative 3 over 2. And then you draw the number line. Here's 0, e to the negative 3 over 2. And then we have to, again, take test points to plug in y double prime, because now you're trying to figure out when y double prime is positive or negative. So give me a number that's between here. What should I use? E to the negative 2, right? Negative 2 is less than negative 3 over 2, so you want to plug that in. How about here?
1.
E to the first part. Oh, 1. 1 is good. Yeah. 1. If you insist, 1 is equal to e to the 0th power, right? Now, if you didn't know why log of 1 is equal to 0, there's a simple explanation. 1 is e to the 0th power. That's why it's equal to 0. Okay, so let's use these values to evaluate y double prime at x equals to e to negative 2 is 2 times ln of e of negative 2 plus 3. ln and e cancels. Negative 2 times 2 is negative 4 plus 3 that gives you negative 1. Y double prime x equal to 1 gives you 2 times ln of 1. I already explained that this is 0 plus 3, so that's equal to 3, which is positive, and that's negative. Okay, so we know that this is negative here and it's plus here. So let's summarize that result here. That before e to the negative 3 over 2, y double prime is negative, and after e to the negative 3 over 2, y double prime is positive. Now, what we established is that because it's decreasing before this point and increasing after this point, at x equals to e to the negative 1/2, you have relative, what? Decreasing before and increasing after. So you have relative minimum. Okay, so this gives you a relative minimum, and there is a change in concavity before this and after this point, so this is an inflection point. So we do have one relative minimum and one inflection point. We need to know where it is exactly. So let's try to figure the points out. So y, when x is equals to e to the negative 1/2, that gives you e to the negative 1/2 squared times ln of e to the negative 1/2. That's e to the negative 1 because these two multiply. And because ln and e cancels, you get negative 1/2. So you get negative 1 over 2e. E to the negative 1 power is 1 over e, right? Maybe I should write here. E to the negative 1 is 1 over e. So this is 1 over e times negative 1/2. If you multiply, you get negative 1 over 2e. Now let's evaluate y at e to the negative 3 over 2. That gives you e to the negative 3 over 2 squared. ln of e to the negative 3 over 2. Again, ln e cancels. This is e to the negative 3 times negative 3 over 2. And that becomes negative 3 over 2e cubed. Again, because negative power means reciprocal, so e to the cube becomes, it goes into the denominator. So those are the y values for the extreme relative minimum and also the inflection point. Let's write down the coordinates. So it's e to the negative 1/2, comma, negative 1 over 2e. That's the relative minimum. And e to the negative 3 over 2, comma, negative 3 over 2e to the cubed. That's the inflection. It's an inflection point. Now let's make a table. When we're making table, we have to decide something. Which one is bigger, e to the negative 1/2 or e to the negative 3 over 2? It's e to the negative 1/2 that's bigger. See, so first of all, 1/2 is less than 3 over 2, but if you put a minus there, it's like that, right? And then if you take the exponential function, it's the same thing. So using that, we can say, we can make a table where x between 0 to e to the negative 3 over 2, and think about y prime value and y double prime value. And then for between 3 over 2 to negative 1/2, we have to think about these values. And after e to the negative 1/2, we have to think about the values. Okay. Now y prime is negative until you get here, so it's negative, negative, and then plus. Y double prime is negative before e to the negative 3 over 2, but afterwards it becomes plus, it's plus and plus. And then the y double prime negative means it's a frowning face, And because it's minus, we're talking about the decreasing part of the frowning face, so it must be going like that. And then over here, y double prime positive means it's a smiley face. And because it's decreasing, we're talking about the decreasing part of the frowning face, so it must look like that. Still, it's not frowning face, sorry, smiley face. So decreasing part of the smiley face gives you that. Now, here's the smiley face, because it's plus, and y prime being positive means you're talking about the decreasing part of the smiley face. So that part. Okay. So that's how you can make use of this two sad clown and happy clown to figure out the behavior of y. All right, so now let's try to draw the graph. I don't know what exactly these values are, but we're just sketching, so it doesn't matter. Let's say this is e to the negative 3 over 2, and this is e to the negative 1/2. And it should be coming down like this, and then going like that, and it should be going up. Oh, by the way, does this have an x-intercept? I should have found the x-intercept. Does this have an x-intercept?
Yes.
Where? When is x squared log of x equal to 0? Either when x squared is equal to 0, but that never happens because x equal to 0 is outside the domain, or when log of x is equal to 0. How do you solve this? Exponentiate both sides. X is e to the 0th power. What's e to the 0th power? 1. So it has an x-intercept then. Okay? So the graph is like this, and the exact coordinates is negative 1 over 2e here, and this is negative 3 over, sorry. This one is negative 1 over 2e here, and then this is negative 3 over 2e cubed. So that's the shape, but we really don't have much idea of what exactly these numbers are. But that's okay. So this is the sketch. Yes?
Can you go over how you got the chart again?
Oh, how I got the chart. Okay. So I established that this comes before that, right? So on the number line, maybe it's good to draw the number line. So here the domain starts at 0. E to the negative 3 over 2 comes first, before e to the negative 1/2. So now these are the special points where something happens to either y prime and y double prime, and therefore you end up with 1, 2, 3 intervals. Okay. So what I'm doing is I'm pointing to the first interval, which is between 0 to e to the negative 3 over 2. Second interval here, and third interval is after e to the negative 1/2. So those are what I'm writing here. And then once I get that down, then you can use this information and say, well, y prime is plus, and then minus, and then plus, right? Minus, and plus, because it changes after e to the negative 1/2. So for y prime, I can just put minus, and plus.
Okay.
Same thing for y double prime. So that's how you figure out the table. Yes?
Just like confirming, the
Mhm.
y prime is the one where it shows direction increasing, decreasing.
Right. Y prime tells you the increasing and decreasing. Y double prime tells you concave up or concave down. And I mean, it's not very hard to remember that y prime positive means increasing and y prime negative means decreasing. What's not so easy to remember is you can get confused about what concave up and concave down means. So we need the help of the two clowns, the sad clown